Hey guys, Mr. Betts here. In the first topic in Unit 10, we talked about infinite series and more specifically convergence and divergence of infinite series and what it means for an infinite series to converge. Now we're going to take a look at a specific kind of series that we should be a little bit familiar with already and talk about what that convergence and divergence is going to look like with geometric series. So let's start with talking about just what is a geometric series. All six of the series that I have on the screen here are all geometric series. And if you look, they all have a pattern where to get from one term to the next, you're always multiplying by the same thing. So in the first example here, to get from 1 to 2, you multiply by 2. To get from 2 to 4, you multiply by 2. So each term in the series, you're multiplying by 2 to get the next one. So we call that a common ratio, and we denote that with an R. So we have a common ratio of 2 in the first one. In the second one, to go from one term to the next, we're multiplying the denominator by 2, and that means that we're multiplying the terms themselves by 1/2. In the third one, to get from each term to the next, we might not think of this as a geometric series normally, but we do multiply each term by -1 to get to the next term in the series. So the common ratio here is going to be -1. The next one, this is not something we would generally think of as a geometric series, but technically it is. This has a common ratio of 1 because to go from 5 to 5, you multiply by 1. The next two have variables in them, but they are geometric series because to go from one term to the next, we're multiplying by z. And in the last one, to get from one term to the next, we're multiplying by -x/3. So a quick way to check if a series is a geometric series is to take any term and divide it by the term before it. So for example, take the second term and divide it by the first term, and then do that with multiple terms. So if we take the second divided by the first, we should get the same thing as if we take the third divided by the second, or if we take the fourth divided by the third. Any term divided by the term before it is going to give us this common ratio here. So every series on the screen is a geometric series, but then we need to talk about what it means then for a series to converge or diverge. So before we do, a geometric series is basically a series in this form right here. So we're going to use sigma notation quite a bit. A naught, naught spelled N-A-U-G-H-T, that means 0 basically. So A sub 0 or A naught is the initial term or the first term. And then R here is going to be what we call that common ratio. And in this sigma notation, as n increments, so as n goes up by 1, then this exponent is going up by 1. And so each time we increment n by 1, we're multiplying by r one more time, and that gives us our common ratio. So let's talk about convergence versus divergence. If you remember from the last topic, we define convergence for a series using the partial terms or the partial sums of that series. So in the series here on the left side, the partial sums are what we get when we add the first n terms together. So the first partial sum is just the first term. So it's what we get when we add the first term together. The second partial sum is what we get when we add the first two terms together. The third partial sum is what we get when we add the first three terms together, and that's going to be 7/4 in this example. And so a series is going to converge if these partial sums approach a particular value. Well, for this particular series, it can be shown that the partial sum is going to be, in the numerators, you might notice that these are powers of 2. So we're going to have 2 to the n minus 1 power. So to get the 2 in the denominator for the second term, that's 2 to the first power, so that's why I'm subtracting 1. In the numerator, this is actually going to be 2 to the nth power and then minus 1. So the numerators here, so say for example the third one, 2 to the third power is 8, 8 minus 1 is 7. 2 to the fifth power is 32, minus 1 is 31. This series of terms, sequence of terms, is going to approach a value of 2. So as n gets really big, the limit of those partial sums is going to approach 2. So we say that this series converges because the partial sums converge to 2. On the other side here, I think it's pretty obvious, but if we look at partial sums, the terms themselves are getting really big. So as we add the terms together, that's also getting really big. So the partial sums themselves are not approaching some finite value, so this series is going to diverge. Now, normally we think of divergence as getting really big, so growing without bound, but a series could actually diverge for another reason. So if we look at this geometric series right here, what's happening is the partial sums are going back and forth between 1 and 0. And then we add 1 and we get 1, and we subtract 1 and we get 0. So the partial sums are not getting really big. They're just bouncing back and forth between 0 and 1. So that's what we call oscillating. So they're not approaching some particular value. So usually divergence, we think of growing really big, but divergence can also mean that it's just not approaching some particular finite value. It could be bouncing back and forth between values, and it wouldn't even have to necessarily look like this. It just means that it's not approaching some particular value. So a geometric series specifically will converge when the common ratio is somewhere between -1 and 1. And you might also see that written like this, that the absolute value of the common ratio is less than 1, that inequality is equivalent. So the geometric series will converge if that common ratio is between -1 and +1. At -1, with a common ratio of -1, that's when we get a series that looks like this one. So we're going to get an oscillating one. If the common ratio is +1, let me go back a couple here, that's going to be a series like this. And as we look at the partial sums in this one, you can tell that the sum's going to be getting really big. So the geometric series will not converge at -1 and +1, but for values between those. So to get the sum of a geometric series, we're going to have a formula here. And this is a formula that you do need to know. And if you look at how this formula is used, I'm going to use it with this sum right here, this series. So the first term is going to go on top. And in this particular series, that's 1. And then we're going to do 1 minus the common ratio. So 1 minus r in this case is going to be, let me write these down here. 1 common ratio is going to be 1/2. So it's going to be 1 over 1 minus 1/2, which does simplify to 2. So the sum of this geometric series is going to be 2. I do need to warn you that this formula will work even if the series doesn't converge. And when I say it works, we can plug in values and we could get an answer, but the answer doesn't actually make sense. So in this second series here, the first term is, again, 1. The common ratio is 2. So we could say the sum is equal to the first term over 1 minus the common ratio, which is going to be -1. It does not make sense to say that these terms here add up to -1. Obviously, the sum is getting really big. So this formula only works if the series converges. If the series diverges, we don't want to try to use this sum formula.